Hey, welcome back to Blendworks, where we're building a game engine with Blender. In this episode, we'll start with slopes that will let us travel up ramps, hills, and stairs, and we'll also add a script to handle user input, so things will actually control like a proper game. Let's take a quick look at where we've been so far. This series is all about using geometry nodes to turn Blender into something that can run games. In the last two episodes, we've built systems that can control our camera, so we can move around our environment. We've added gravity, collision with objects, running and jumping, and we have a pretty good foundation to work off of, but we still have a ways to go before we have a proper game engine. Links to those previous episodes are in the description. So let's jump right into slopes. If you've never worked with the back end of games before, you might not be familiar with the joys of dealing with slopes. We come across them all the time in real life and in games, so we usually take them for granted. Turns out that dealing with simulated slopes is actually really interesting, but can get a bit complicated. First, let's see what happens if we put a slope into our game without making any changes. We just walk through the slope until our collision raycast detects it, and then we stop moving. If we move down the slope, we try to move flat until the floor raycast loses contact with the floor, and then gravity takes over, resulting in this jittery descent. If you think about moving up a slope, and use a vector to describe it, that vector is moving parallel to the slope. Up to this point in our game, all the surfaces that we could walk on were totally flat, so our movement vector, or the direction that we're moving, has always been parallel to the ground. In theory, the solution to our problem is to find out how much the slope is rotated off of our floor, and rotate our movement vector by that amount, so we can stay parallel to the slope as we travel up. We'll need two vectors for this, one for the floor, and one for the slope. Getting these vectors will actually be pretty easy in our situation since we already have almost everything we need. The floor vector is super easy since that's the same as the global z-axis, which is just the direction that up is. Our other vector depends on the specific slope we're encountering, so we'll need something that can determine the slope vector on a case-by-case basis. Slopes are just faces, and faces all have normals. Normals are vectors that are perpendicular to their corresponding face. They have several uses, but for us, they're exactly the vector we need. We just need a way to get them. In the last episode, we looked at raycasts, which we can use again to get the face normal from any mesh by plugging in that mesh, then pointing the raycast at the face that we want. Since we already have a raycast pointed down at the floor to check if we're touching the ground, we don't even need to add anything. We can just pull the hit normal from that. Now that we have our two vectors, we can find the angle between them. But it's not quite as simple as finding a single degree of rotation between two vectors. We have worked with rotating vectors before, but so far we've only rotated on a single axis. For example, we rotate our player movement vector to change the direction we move by rotating along the z-axis, which is done with a single value or degree of rotation. There are actually quite a few ways to rotate in 3 dimensions, but the one we'll be using this time is Euler angles. We'll get the chance to work with some of the other methods later in some different situations. Euler angles, or just Eulers as I'll be calling them, contain a set of 3 numbers that define rotation on each axis. Eulers are something that we can use on a vector, which results in a new rotated vector. Now it's important to note that just like vectors, Eulers have 3 sets of numbers, but they aren't the same thing. Newer versions of Blender help make this distinction more obvious by giving vectors a dark purple color and rotations a lighter purple. At its core, Eulers aren't any different than rotating on one axis, then rotating the resulting vector on a different axis, and then doing that again on the third axis. The tricky part here is that rotations have to be done in order, one after the other. You can't just rotate everything all at once. Because Eulers have an order, subsequent rotations will affect previous rotations. Depending on the situation, you can rotate in different orders. For example, you could rotate on the z-axis first, but we use XYZ Eulers, which rotate the x first, then the y, then the z. You can see here that the x-axis is rotated, and then when the y rotates, it also rotates the x. And then when we rotate the z, it rotates both the y and the x. So that's cool and all, but how do we actually use this? We can put Eulers to work with the align Euler to vector or align rotation to vector node, which do the same thing. It was just updated in Blender 4.2. I've still been using Blender version 4.1.1 since I prefer the older Eevee rendering, but just note that the two nodes are interchangeable. The node takes a vector as an input and outputs a rotation. It calculates the Euler rotation between whatever vector you plug in and the X, Y, or Z axis. We'll select the Z axis at the top of the node since that's our up direction, and we can just plug in our hit normal from our floor raycast. Now that we know the slope's rotation, we can apply it to our player's movement vector. We'll just take the output rotation of our align Euler to vector and plug that into a rotate vector node, and then plug in our player movement vector, and now we have a working slope system. It's a lot of theory involved in just 2 additional nodes, but understanding how to rotate vectors in 3D space is super useful. We'll use it a lot going forward, so it's important to understand the basic concept behind it. In a later episode, we'll be adding planetary gravity, which ended up taking like 4 or 5 months to figure out, but it was some of the coolest stuff I've ever worked on, and I'm really excited to make an episode about it. If you're anything like me, you find it easier to understand something by playing with it in real time. So I made a visualization tool that makes it easier to understand how the align rotation node works, which is up on my Patreon, or is also available with the pro version of my vector visualizer tool. It shows a visual of the rotation on each axis and lets you see how the axes are moved around based on their position in the hierarchy. So before we move on to the script, let's add a couple of extra features to our slopes. One problem that we have is that we could climb some pretty steep slopes, which we might not necessarily want. Dipping our toe into some more math for a second, we can use the information that we already have to calculate how steep the slope is, and then we can limit our maximum climbable slope. To find the angle, we can use the arc cosine of the dot product of our 2 vectors, which outputs a single angle as a radian. We end up using a lot of dot products when we work with vectors. They're pretty straightforward though. We're just multiplying the x of our 2 vectors, and then adding that to the multiplied y of both vectors, and then adding that again to the multiplied z of the 2 vectors. They're useful because they give us information on how vectors are oriented in relation to each other. We can use our freshly calculated angle to figure out how steep a slope we're on and limit the maximum. We can just add a node that checks if the angle is over a certain number of our choosing, and then plug that into a switch that stops us from moving. And the cool thing here is that if we wanted to, we could also use our steepness value to change things like the walking speed based on the slope we're on, and probably some other cool stuff too, but we won't worry about anything like that right now. We still need one more piece of information to get our slope limiter working. We'll need another calculation to check if the slope is downward or not. Otherwise, we won't be able to move at all if we touch a slope that's too steep. We can use the same dot product formula again, but we'll use our post-rotation movement vector instead of our slope vector. So this will let us measure the angle away from our universal up direction. If the player movement vector is more than 90 degrees away from 0, 0, 1, then we can determine that the slope is negative, since it's more closely aligned with the ground than it is towards the sky. And just one more thing before we move on. If we want to add actual steps to our slope, our raycast can handle it pretty well, but it's still pretty jumpy, and each step moves the camera along with it. If we want to have the steps but keep our travel smooth, we can just separate the mesh that makes up the steps and put it in a separate non-collision collection that the floor raycast doesn't read. The steps will still render and look good, but we won't have to deal with the jumping. So now that we have slopes in our game, we can use the same concept to climb all sorts of stuff. Even with our shiny new feature, our game is still barely usable because you still have to control everything by sliding stuff on the geometry node panel, which obviously isn't a great experience. Thankfully, Blender has a built-in scripting system and a Python API that allows us to handle keyboard and mouse input. We're using these scripts as a middleman that collects input from the user and passes them on to the geometry nodes that we've already built. Now it's worth noting that I really wanted this project to be made almost entirely with geometry nodes, but this is one of the exceptions that I had to make because handling windows and user inputs is just one of those things that nodes aren't really meant to do. But the nodes are still doing all the heavy lifting as far as the functional side. The script just makes it easier for us to interact with them. So the Blender Python API has tons of useful stuff, and a lot of it comes in handy for our script. A deep dive into every line is outside of the scope of this video, so let's do a lightning round and just do a bird's eye look at what the script is doing. Also, don't tell anybody, but I'm not a super great coder or anything, so feel free to tear apart my code in the comments. First, we define a bunch of things so that we can use them later. Then we start the timeline so that the animation is playing if it's not already. We set a window with a set resolution and then change the view to the camera. And we need some extra lines to get the camera to fill out the screen. Then there are a bunch of lines to individually disable aspects of the overlay, which we can add individually one by one if we need them. Some of the nodes get set with a default value to start with as well, just to clear any unnecessary input. For example, we'll clear any movement inputs so that we don't start walking right as the game starts. We allow the mouse to continue moving even after it hits the border of the screen, and then we create the main loop of the script, which continues to run until the escape key is pressed. If the escape key is detected, then the animation is stopped, and I have some toggles on the menu that can optionally start the timeline over again or close the window if the loop ends. If no escape key is pressed, then the loop just continues to wait for input. Mouse input is at the top of the loop, which gathers the mouse coordinates and then updates anytime the mouse moves. These values are passed into the nodes that handle the camera look after they're divided, since they move pretty quickly otherwise. The number we divide by acts like a mouse sensitivity adjustment. For the other inputs, we use event.type to trigger parts of the script when certain keys are pressed or when they're released. Most of the time, they're just preset values that get put into the node inputs. For example, if the script determines that the W key has been pressed, it sets the value of geometry node socket 2 to 0.01, which is the socket that's responsible for forward and backwards movement. If the W key is released, then the value is set back to 0.00, which stops the movement. Other inputs change a Boolean instead of a number, like the spacebar to jump or the shift key to run. You'll notice that the script can access node inputs with a socket number, and you can view the number of whatever input you want by looking for it in the info window after changing the value of that input. I have the F5 key set to toggle the show FPS switch, which has some extra bit of code that first checks whether the switch is true or false already, and then changes it to the opposite of the current setting. And the actual code that functionally handles the FPS overlay lives in a different context later in the script. So then we set the shading type to render to show off all of our beautiful texturing and shading. We disable the mouse cursor. Then we set the FPS toggle on or off based on the switch that we just set. And then lastly, we make some closing statements. Then at the very end, we can make the window full screen if that option has been selected from the node panel. And that's the script. As you might imagine, there are plenty of specifics that I glossed over, just in the interest of keeping the video short and relevant. So if you have any questions, just let me know in the comments. Now that we're 3 episodes in, we're definitely getting closer to something that can be used to make a proper game. In fact, the video I recently put out where I made Minecraft in Blender runs on a version of blendworks that's pretty much the same as the one in this video. It just has some extra stuff to handle the game specifics, like placing blocks. I'm really excited to continue to add features, so stay tuned for future episodes. As always, I'll leave the project files up on Patreon. Thanks so much for watching my video, and I look forward to seeing you in the next one.